Hi, I'm Josh, and I'm excited to present alpha invariance on inverse scaling between distance and volume density in neural radiance fields. This work was done with collaborators at TTI Chicago and Purdue University. In NERF, the task is novel view synthesis, where the input is a set of images and their known camera poses, and the output is a learned scene representation that can render images at novel viewpoints. NERF renders images via differentiable volume rendering and optimizes a function f that maps from spatial position and viewing direction to radiance and density. The objective is to then minimize the L2 image reconstruction error on the training dataset. To perform volume rendering, we first cast a camera ray through each pixel into the scene. Next, we sample points for their densities to compute the opacity and transmittance of each segment. These are then integrated over the entire array to get the final pixel value. The contribution of each segment to the final rendered color is called its weight, which is often used to refine the sampling strategy. Note that density is learned while distance is not. Volume rendering presents a complication due to an explicit integration over space, i.e. the delta term, and the dimensions of this space lose meaning. So our key question is, what are the units of the measuring ruler? For a multiplicative factor k applied onto delta, it is sufficient for the probability density w, and thus sigma to scale by a factor 1 over k in order to maintain an identical alpha value. As a result, alpha is solely dependent on the geometry of the scene, not the scale at which it is represented in the model. We call this phenomenon alpha invariance. How do we maintain alpha invariance? In this expression, x is the raw output from the underlying neural field. It must be rectified so that it is non-negative. So, which activation function do we use? Well, the literature uses three: ReLU, softplus, and exponent. Here, we plot alpha as a function of the raw output x and interval length d for each of the three activation functions. In practice, we find that models using ReLU and softplus to rectify x use brittle heuristics to stabilize optimization. Our recommendation instead is to parameterize density with exponent. As seen in the rightmost plot, exponent leads to a smooth sigmoid-like transition from low to high alpha values regardless of the interval length d. There are several issues with using exponent, however. First, as scene size grows, then density needs to shrink to maintain identical local alphas. But exponent grows exponentially quickly, so it struggles to learn small values, leading to high alpha values everywhere in an opaque scene. Second is numerical instability. Exponential values can quickly grow to infinity, leading to numerical overflow and NaN values during training. People have addressed it by clipping the gradient values in the backwards pass, but this is still insufficient. To solve these issues, we develop a high transmittance initialization, which forces the scene to be initially transparent. Recall that transmittance is related to density as such. The inner integral gives a Monte Carlo estimate that converges to the expectation of sigma over the entire array. Replace the left-hand side with t prime, an initial transmittance target such as 0.99. Now, assuming that sigma is drawn from a normal distribution with mean mu and SED tau, we can solve for the expectation. Plugging this expression back into the first equation. Now let's solve for mu. This is our desired high transmittance target at initialization and is added to the raw output x from the underlying neural field before applying exponent activation. This expression is discretization agnostic. The sampling resolution doesn't matter, only the scene size L. Now we demonstrate alpha invariance. Start with the volume rendering equation, replace sigma with exponent, add our high transmittance target mu to x, absorb delta as a logarithmic offset to x plus mu, which helps with numerical stability, expand the expression for mu, and finally, combine the two terms representing distance, delta and L. Note that any scaling on delta is matched with an identical scaling on L, so this term becomes constant and alpha is now invariant to scene size. Note that x also becomes invariant to scene size. We now demonstrate the efficacy of our method. We query a grid of samples for their local alpha values from TensorRF trained at various scene scales on the Blender dataset. TensorRF suffers from opaque scenes at larger values of k when no initialization is applied, as seen by the sharp reduction in transparent samples, while our offset effectively addresses this issue even at very large values of k. Qualitatively, our method also vastly improves the renderings of the NERF factor architecture at large scene scalings. On large indoor and outdoor scenes, not using our high transmittance offset causes the optimization to get stuck with cloudy floaters, while using our strategy produces clean RGB images and depth maps. Thank you. Please visit our project webpage for more information.